Welcome back to Sequence and Series. This lecture is intended to explore some more problems on these topics. What is the sum of all 3-digit numbers that leave a remainder of 2 when divided by 3. To start with, let us have the following observation. Let a plus 1, a plus 2, a plus 3 be consecutive positive integers. Further, if a is divisible by 3, then a plus 1 will leave remainder 1 when divided with 3, whereas a plus 2 will leave a remainder 2 when divided by 3. This is a trivial but useful observation. Let me repeat. If you have a plus 1, a plus 2, etc. to be consecutive positive integers with a divisible by 3, meaning it leaves remainder 0 when divided by 3, then a plus 1 will leave remainder 1, a plus 2 will leave remainder 2, then the next number a plus 3 will be again divisible by 3, and so on. On the other hand, if a is not divisible by 3 but leaves a remainder 1 when divided by 3, then a plus 1 will leave remainder 2 when divided by 3, whereas a plus 2 will be exactly divisible by 3, and so on. Keeping this observation in mind, let us proceed with solution of given problem. You are asked to find sum of all 3-digit numbers that leave a remainder of 2 when divided by 3. The first 3-digit number, namely 100, leaves remainder 1 when divided by 3. Therefore, the next 3-digit number leaves remainder 2 when divided by 3. That is, our observation is that the first 3-digit number which leaves remainder 2 when divided by 3 is 101. Then the next number, namely 102, will be divisible by 3. 103 will leave remainder 1 when divided by 3, whereas 104 will leave remainder 2 when divided by 3. Thus, the numbers, more specifically 3-digit numbers, which leaves remainder 2 when divided by 3 are 101, 104, 107, etc. Let us try to find the last 3-digit number which leaves remainder 2 when divided by 3. Note that the last 3-digit number or the highest 3-digit number is 999, which is divisible by 3. So, the next preceding number, namely 998, will be leaving a remainder 2 when divided by 3. Therefore, the last number in this succession of numbers is 998. Consequently, the question reduces to find the sum of all terms of the sequence 101, 104, 107, etc. up to 998. Can you observe that this sequence is in arithmetic progression with common difference 3? Therefore, we are asked to find sum of finite number of terms of an AP with first term 101 and common difference 3. Recall the formula that is available for sum of first n terms of an AP. There are two formulas available, one being sum of first n terms of an AP equal to n by 2 multiplied with the sum of first term and last term. There is one more formula. However, note that any of these two formula requires n, the number of terms that you are summing. Therefore, the first task is to find how many terms are there in the AP starting from 101 and ending with 998. In other words, what is n involved here. To tackle this, let 998 be the nth term. Then 998 will be equal to a plus n minus 1 times d. We know the first term a is 101 and the common difference is 3. Simplifying this equation, we get n minus 1 equal to 998 minus 101 divided by 3, which is 299. Therefore, n will be equal to 300. Thus, in the given sequence 101, 104, etc., 998, which is an arithmetic progression, there are in fact 300 terms. Hence, we are asked to find sum of first 300 terms of an arithmetic progression. Therefore, required sum is equal to n by 2 into first term plus last term is equal to 300 by 2 multiplied with 101 plus 998. With a little computation, one can obtain the answer as 164,850, 1,64,850. This solves the given problem. Let us proceed with a similar problem. Obtain the sum of all positive integers up to 1000 which are divisible by 5 and not divisible by 2. This is again a problem dealing with sum of first n terms of an AP, as one can see. Let us formally solve this. Note that positive integers up to 1000 that are divisible by 5 are 5, 10, 15, etc. 1000. Note that 1000 is divisible by 5. The preceding number divisible by 5 will be 995. In this list, note that 10, 20 and so on are divisible by 2. Hence, we should not consider 10, 20 and so on, while listing positive integers that are divisible by 5 but not divisible by 2. Five, 15, etc. We are asked to positive integer up to 1000. So, the last positive integer under consideration which are divisible by 5 but not by 2 will be 995. Thus, the problem boils down to find the sum of terms of the sequence 5, 15, so on up to 995. One can easily observe that this sequence is an arithmetic progression with first term 5 and common difference 10. As in the previous problem, let us recall that sum of first n terms of an AP has two formulae. However, both needs the number of terms that are required to be summed. Therefore, as next step, we shall find how many terms are there in this AP starting from 5 up to 995. To this end, let 995 be the nth term. Using the formula for nth term, we get 995 is equal to a plus n minus 1 times d, which is 5 plus n minus 1 times 10. Isolating n, we get n equal to 995 minus 5 by 10 plus 1. That implies n equal to 100. Thus, 995 in the given list is in fact the 100th term. Using this required sum, that is sum of first 100 terms of an AP with first term 5 and common difference 10 will be n by 2 into first term plus last term. We shall rely on this formula since last term is known to us. This is 100 by 2 into first term is 5 and last term is 995. With some simple calculation, one can get the answer to be 50,000. Here is your next problem. If A is given to be 2 power 65 and B is given to be 2 power 64 plus 2 power 63 plus etc. plus 2 power 0, then is A greater than B? In this problem, you are asked to compare A and B. Towards the solution, first let us observe that B, which is given to be 2 power 64 plus 2 power 63 plus etc. plus 2 power 0, is in fact sum of first few terms of a GP with first term 2 power 0 and common ratio 2. B is sum of terms of a GP with first term A equal to 2 power 0, which is 1, and common ratio 2. See that 2 power 0 is the last term, last but 1 will be 2 power 1, preceding to it will be 2 square and so on up to 2 power 64 if you read from the other side. Therefore, you can observe that the first term is 1 and the common ratio is 2. Now, let us use the formula for sum of terms of a GP. Recall that sum of first n terms of a GP with first term A and common ratio R is Sn equal to A into R power n minus 1 by R minus 1, assuming R not equal to 1. Therefore, similar to previous two problems, first task will be to find out how many terms are there in this series. To find out, let us assume that 2 power 64 is nth term when we read from the other side. Let 2 power 64 be the nth term. Using the formula for nth term of a GP, A into R power n minus 1 is equal to 2 power 64. Note that A is 1 and R is 2. Recall the law of integers. Here the base is same 2 and numbers are same. Therefore, comparing the exponents, one gets n minus 1 equal to 64, isolating n equal to 65. This concludes that there are in fact 65 terms in the sum 2 power 0 plus etc. up to 2 power 64. Using this, let us find B. B is equal to A into R power n minus 1 by R minus 1 being sum of n terms of a GP, which is equal to A is 1 times R is 2, so 2 power 65 minus 1 by 2 minus 1, which is 2 power 65 minus 1. Therefore, we obtain B to be 2 power 65 minus 1. Recall that 2 power 65 is the value of A. Therefore, B is A minus 1, which says that A equal to B plus 1. Consequently, A is greater than B. Note that A, B are positive. Thus, answer to the question is yes. A is greater than B. Here is the next problem for you. A piece of equipment cost a certain factory rupees 6 lakh. If this equipment depreciates in value 15% the first year, 13.5% the next year, 12% the third year, and so on. What will be its value at the end of 10 years? All percentages applying to the original cost. You have a piece of equipment with certain cost. It depreciates in value every year. We are asked to find the value at the end of 10 years. Since all the depreciation is given in percentage, for the sake of simplicity, let us assume that the cost is 100. In that case, the percentage of depreciation at the end of 1, 2, 3 years are given in the list 15, 13.5, 12, etc. This list of percentage of depreciation can be observed to be in arithmetic progression with first term A equal to 15 and common difference D equal to minus 1.5. It is difference, the second term minus first term, or the third term minus second term, and so on. Keeping this observation, let us find what is the percentage depreciation at the end of 10 years. Therefore, percentage of depreciation in 10th year. This is simply asking the 10th term of this AP. Consequently, the percentage of depreciation in 10th year can be obtained from the formula A plus 9D. Substituting the value of A and D, we obtain the percentage depreciation in 10th year to be 1.5. Therefore, the successive depreciation in the first 10 years would be 15, 13.5, 12, etc. up to 1.5. Using this, total value depreciated in 10 years, assuming the cost to be 100, is 15 plus 13.5 plus etc. plus 1.5. Can you see that this sum is in fact sum of first 10 terms of an arithmetic progression? Therefore, its value will be 10 by 2, 10 being the number of terms in this sum, multiplied with 15 plus 1.5, which is 82.5. Therefore, assuming the value to be 100, total value depreciated in 10 years is 82.5. As a consequence, value of the equipment at the end of 10 years would be the cost 100 minus total depreciated 82.5. Thus, the value of the equipment after 10 years would be 17.5. This is the case if the cost is 100 rupees. Now, let us scale it with the actual cost. Total cost being 6 lakh, its value at the end of 10 years would be 6 lakh into 17.5 by 100. This is because 17.5 is the depreciation if the cost is 100. Therefore, 17.5 by 100 is the depreciation if the cost is 1 rupee. Multiply it with 60,000, the actual cost. This can be simplified to 1,05,000. This completes the solution. Let us proceed with few more problems. If log 2 log 2 power x minus 1 and logarithm of 2 power x plus 3 are in AP, find the value of x. This is an interesting problem based on arithmetic progression and the concept of logarithm. To set the stage for it, first let me remind you some basics on logarithm. Recall that logarithm is inverse of the process of exponentiation. More precisely, logarithm of a positive real number x is the exponent to which another positive real number should be raised to obtain x. In simple, logarithm of a positive real number x to base b, where b is a positive real number other than 1, is y if b power y is x. I repeat, logarithm of a positive real number x to the base b, where b is a fixed positive real number not equal to 1, is said to be y if b exponentiated with y gives x. For instance, we know 2 power 3 is 8. In logarithmic language, we say this log of 8 to the base 2 is 3. As another example, we know 5 square is 25. In the language of logarithm, logarithm of the real number 25 to the base 5 is 2. We know 25 power 1 is 25. Therefore, logarithm of 25 to the base 25 is 1. Please compare. Logarithm of 25 to the base 5 is 2, as 5 when squared gives 25. At the same time, logarithm of 25 to another base, namely 25, is 1. Let me give you one more instance, just to give some specific example. We say logarithm of 9 to the base 3 is 2. That is because 3 when squared gives 9. I urge you to practice more with exponentiation and its inverse process, logarithm. Let me just remark that though I have defined logarithm of a positive real number x with respect to a positive real number b not equal to 1, or more specifically with base b not equal to 1, it is customary to take b as the number e. In that case, we call the logarithm as natural logarithm. Logarithm of a number x to base e will be called natural logarithm of x. It is worth to recall that in calculus, it is preferred to work with natural logarithm than logarithm to an arbitrary base b. And natural logarithm is denoted by the symbol ln. Next, let me recall two basic properties of logarithm. Logarithm of product of two positive real numbers x and y to a fixed base b is sum of logarithm of the individual. Logarithm of a product gets transformed into sum of the logarithm. In fact, this simplifies the calculations, and this property is one of the motivations for defining logarithm. The complicated process of multiplication can be changed to a relatively simple process of addition by taking logarithm. And as next property of logarithm, let me recall that logarithm of a power x power p to some base b not equal to 1 is p times logarithm of x with respect to base b. To put in simple language, logarithm changes product to sum of the logarithms, and logarithm changes power to the product. Keeping this in mind, let us come back to the problem. Given that log 2 power x minus 1 and log 2 power x plus 3 are in AP. Since these three numbers are in AP, the number appearing in the middle, namely log 2 power x minus 1, would be arithmetic mean of the numbers occurring in the first and third place. That is, therefore, twice logarithm of 2 power x minus 1 is log 2 plus log 2 power x plus 3. Now, let us use the property of logarithm. Logarithm of 2 plus logarithm of 2 power x plus 3 can be written as logarithm of the product 2 into 2 power x plus 3. Similarly, in the left hand side, 2 times logarithm of 2 power x minus 1 can be written as logarithm of 2 power x minus 1 the whole square. Thus, the given information translates to logarithm of 2 power x minus 1 the whole square is equal to logarithm of 2 into 2 power x plus 3. Now, taking exponent and bearing that logarithm and exponentiation are inverse process, we get 2 power x minus 1 the whole square is equal to 2 into 2 power x plus 3. Let us expand this to yield 2 power x square minus twice 2 power x plus 1 is equal to twice 2 power x plus 6. With simple manipulation, this transformed to 2 power x the whole square minus 4 times 2 power x minus 5 equal to 0. If you let 2 power x to be y, it can be seen that the previous equation is a quadratic equation. Y square minus 4y minus 5 equal to 0. Solving, we get y equal to 5 or y equal to minus 1. Substituting y equal to 2 power x, this reduces to 2 power x equal to 5 or 2 power x equal to minus 1. For a real x, note that 2 power x cannot be minus 1. Therefore, 2 power x will be equal to 5. Recalling the definition of logarithm, this is same as saying x equal to logarithm of 5 to the base 2. Let us conclude with this problem. Thank you.